Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 5th, 2026, just 2 days ago. It unifies the chaotic landscape of autonomous AI into a coherent framework, proposing a new agent transformer abstraction that helps systems transition from passive chatbots to active, tool-using operators. The paper is titled AI Agent Systems, Architectures, Applications, and Evaluation. And, as we'll see later, the breakdown of orchestration patterns and design trade-offs offers a really impressive roadmap for building reliable agent deployments. To get us started, Figure 1 maps out the high-level landscape. The top row identifies 3 key drivers. First, the expanding scope from writing assistance to workflow automation. Second, the need to handle long-horizon tasks where errors compound. And third, rising safety pressures. Below that, the figure highlights enabling trends, including foundation models, tool calling, and reasoning orchestration that all converge to make practical agent systems a reality. While Figure 1 maps the broad landscape, Figure 2 defines the core architecture. This diagram presents the agent transformer abstraction, placing the foundation model as the central brain. In the top section, the policy core interacts with 4 essential modules: perception, memory, planning, and action tools. Below that, the workflow translates this theory into a practical deployment recipe, guiding developers from initial integration through operation and finally to evaluation. So, Figure 3 details that engineering process, laying out a 3-step cycle for building these systems. It starts on the left with model choice, where you select a capable backbone like GPT-4 or Claude 3. Then, the central block focuses on interface design, which is crucial because it constrains the model by defining strict tool schemas and canonical action templates, essentially turning open-ended text into safe, typed actions. Finally, the process moves to evaluation on the right, where performance and safety are validated to drive iterative refinement. Well, while the previous figure focused on the engineering lifecycle, Figure 4 presents the multi-layered learning stack. On the left, the diagram organizes the hierarchy into 3 levels, starting with strategies and prompts at the top, passing through the agent system infrastructure, and grounding everything in the foundation models at the bottom. Moving to the right side, we see the major constraints these systems face, such as long-horizon decision-making and safety requirements. The connecting arrows emphasize that every learning choice must directly address these operational challenges. Okay, moving deeper into system dynamics, Figure 9 reframes the challenge as an explicit optimization problem. The central graphic illustrates the core trade-offs, balancing reliability against latency and cost using these 3 weighing scales. To manage this equilibrium, the bottom panel shows orchestration policies, where developers tune sliders for tool selection and verification depth. Finally, the right side details search-based planning, demonstrating that exploring tree-structured action paths improves performance on hard tasks, effectively trading higher compute for greater reliability. So, while the previous figure optimized the system at runtime, Figure 11 backs up to the training pipeline itself. The diagram splits development into 2 pillars, pre-training on the left and fine-tuning on the right. The blue panel highlights that pre-training now incorporates multimodal data and tool-related objectives, teaching the model to recognize API structures early on. Moving to the orange panel, fine-tuning then refines this for active use, utilizing methods like RLHF to enforce safety. Crucially, the bottom section introduces trace-centric fine-tuning, where the model learns from full interaction histories to plan, verify, and recover, rather than just answering questions. Alright, having established the training pipeline, Figure 18 zooms out to the entire application landscape. At the center sits the core agent architecture, acting as the operational hub that radiates capabilities like planning and perception outward. The left side highlights industry and physical systems, where agents handle autonomous coding and robotics tasks that demand precise tool execution. Conversely, the right side covers gaming and specialized domains, like healthcare, which prioritize interaction and high-stakes reasoning. Finally, a red ring of cross-cutting challenges, including safety risks and evaluation barriers, encircles the whole system, emphasizing that deployment difficulty spans every sector. Wrapping up, the critical insight is that capability gains are shifting from model scaling to system design. To build agents that truly operate in the real world, developers must focus on architecture, specifically memory, tool schemas, and verification loops, rather than just raw intelligence. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.